Okay, I guess this session was to start at 7, so it's a few minutes after 7. I guess I can start. It's okay. All right. So my name is Ray O'Neill. I'm a professor of physics and astronomy at Florida A&M University. I'm the director of the Astroparticle and Cosmic Radiation Detector Research and Development Laboratory. And I like to call it my own hackerspace in the academic arena. And this talk is as much sharing with you a project I'm excited about as much as a plea for involvement, for participation as well. So I should say before I get started, this is a very special year for cosmic rays. Many of you may be aware that this is the 100th anniversary year of the discovery of cosmic rays by Victor Hess. Victor Hess originally discovered cosmic rays from the spontaneous discharging of electroscopes that were left just sitting. He decided a bold experiment near the turn of the century to take a balloon flight with electroscopes and measure their rate of discharge at various altitudes. And so from that, he determined that the radiation causing this discharge was definitely coming from space. The history is very interesting. Robert Millikan, who's responsible for determining the charge on the electron, sort of created a public argument that was documented by the New York Times, in fact, between Hess and Millikan about whether this radiation actually was coming from space or whether this discharging was a property of air itself. So it's kind of an interesting, if you're interested in the history, you should definitely look into it. Well, 100 years of cosmic ray research has gone by. We've learned a lot about the nature of the cosmic rays, but there are some questions that continue to plague the community and are not quite answered yet, and it's primarily the sources of the highest energy cosmic rays, whether the highest energy cosmic rays at the end of the known cosmic ray spectrum are extragalactic in origin or galactic in origin. The most recent data seems to indicate that they are extragalactic in origin. However, there's still a lot of uncertainty with regard to the actual sources in terms of the astrophysical sources that the particles are coming from, whether they're coming from active galactic nuclei, black hole, creation events, neutron star creation events is associated with supernova and other star death events, and possibly exotic events associated with the decay of dark matter particles, which the LHC may sooner rather than later provide us with the data for that, as they have already seemed to have found discovered signals that seem to point to the Higgs particle. Okay, so the cosmic ray spectrum to date. So that you can see that the cosmic ray spectrum, and this is when I talk about the cosmic ray spectrum, I'm pretty much going to limit the discussion to charged or neutral particle cosmic rays, not gamma rays, not high energy light, which of course is associated with cosmic ray events, and in fact gamma ray astronomy is a marker for locations in which cosmic rays may be being created and accelerated in astrophysical sources. But anyway, the spectrum covers a broad range of energies, more than 10 orders of, more than 10 orders of magnitude, the order of 10 orders of magnitude in energy in electron volts. You can see that at the ankle, beyond the ankle the data points become few and far between, and that's because those events are extremely rare. They're extremely rare. It's not clear why they are rare. They may be rare because the acceleration mechanisms, the astrophysical acceleration mechanisms, sort of peter out at those energies, or we're just not looking enough. We don't have enough observations to provide for a large number of statistics, and that's really what this project is really all about, is increasing the statistics. So the cosmic rays consist of protons, antiprotons, positrons, electrons, neutrinos, antineutrinos, nuclei, and I put a question mark on the anti-nuclei. There is at least one experiment that was created specifically to look for anti-helium in the cosmic ray spectrum, and that experiment is now installed on the International Space Station. And it's already taken quite a bit of data, all null events so far for anti-helium. If anti-helium were discovered in the cosmic ray spectrum, or any anti-nuclei were discovered in the cosmic ray spectrum, that would completely rewrite what we think we know about the structure of the cosmos. Basically, it would mean that there are anti-stars. Because any helium that originates from the space environment would have to have been created in stars. It's unlikely that helium would be primordial helium created in the Big Bang nucleosynthesis. And so that would mean that there's a whole region of the universe that's the sort of antimatter, and it's separated from the material universe. I apologize for the anti-people and the anti-matter universe, because to us, we are the antimatter, right? So anyway, Richard Feynman had a really funny joke about that, about how to determine whether an alien that you may be communicating with is composed of antimatter. The antimatter has the opposite spin angular momentum states, quantum states, and so once you communicate with the alien species and you agree on what is left and right and up and down, and they come and visit you, and then they come out of their spacecraft, and if they then raise their left hand to shake your hand, then don't touch them. Yeah. Okay, so the specific cosmic rays of interest of this particular project are the so-called UHECers. The ultra-high energy cosmic rays, these are the cosmic rays that exist at the very end of the energy spectrum, beyond the ankle of the spectrum. So the National Academy of Sciences, in their New Worlds, New Horizons review, which was part of the decadal survey of astrophysics, has indicated a number of important remaining questions for cosmic rays. And they pretty much are, what are they, right? In other words, are the highest energy cosmic rays, are they actually the particles that we think they are, the normal subnuclear particles, or are they something else? Where do they come from? How are they accelerated to such high energies? And are they actually indirect markers for dark matter? So in other words, do the particle cosmic rays at the highest energies come from the actual decay, self-annihilation decay of the so-called weakly interacting supersymmetric massive particles that the LHC should find very soon? If they don't, then actually there's a problem, because they've already found the Higgs, if indeed they found the Higgs. So just to highlight the review by the National Academy, the origin of cosmic rays is still a mystery. The features so far in the data seem to point towards an extragalactic origin. However, more precise determination of the degree of anisotropy, which may be possible with improved statistics. So the degree of anisotropy, that is that they're coming from some places in the sky more often than other places in the sky. Okay, so a little bit of review on propagation of the ultra-high energy cosmic rays. So the discovery of cosmic ray energies beyond a certain energy limit is puzzling because of the GZK effect. So what the GZK effect is that it's this effect that basically it's a negative feedback mechanism on the energy of propagating cosmic rays in the universe. If a cosmic ray particle is so energetic, then due to relativity, relativistic transformation, right, in the frame of the particle, then the background light of the universe should look much more energetic, right? So the microwave background, the radio, microwave, visible gamma ray, diffuse gamma ray, and diffuse X-ray background should seem even more energetic, relativistically transformed in the frame of the ultra high energy particle, and therefore the ultra high energy particle is being bombarded by these extremely high energy photons in its frame, right? And so that will instantiate a delta, what's called a delta resonance, if the particle is a subnuclear particle like a proton. Then the gamma rays are actually interacting with the quarks, and so this causes a decay of the particle, and so much of the energy then is lost to the decay products, and so you would not expect to measure particle cosmic rays beyond a certain energy because of this very effect. Now, it turns out that you can use this effect as a way to measure distances, right? So if the particles are created by sources at a certain distance, right, from the from the galaxy, or within the galaxy from the solar system, then basically they can only go so far before this effect becomes more probable than less, right? Okay, so detection of cosmics, right? If they're energetic enough, then they will not be deflected very much by the galactic magnetic fields. And so they will pretty much point back to their sources. So if we can detect them and determine where they're coming from, basically detect the shower front, I'll talk about showers in a minute, then we're basically pointing towards the astrophysical source of the cosmic rays. And again, the suppression of distance source background flux by the GZK effect. So any sources that are beyond, I think 100 megaparsecs we will not be able to see at the highest range of the energies because the GZK effect will have dissipated all of that energy. Which is a good thing actually for astronomy, for particle astronomy, because then any nearby sources will stand out like a sore thumb. Okay, so the main way of detecting the ultra high energy cosmics is through the extensive air showers, where you're actually using the Earth atmosphere as part of your detector volume. And so when these ultra high energy particles interact with the atmosphere, they generate a shower of secondary particles and photons, and those secondaries can be detected at the ground by various techniques. And there are two sort of parts of a shower. There's the hadronic part, which is the nuclei-initiated, and the electromagnetic, which is the gamma ray initiated. So for instance, if you have a high energy gamma ray that enters the Earth atmosphere, it will essentially generate electron-positron pairs and more photons, and electron-positron pairs and more photons, blah, blah, blah. You get a cascading shower. However, a hadronic shower, which is initiated by a proton or a nuclear fragment like iron or oxygen that hits the atmosphere, will generate other fragmented nuclear fragmentation and subatomic particle showers, plus an electromagnetic component. And so I'll just skip this. You get the point. The idea here is that one way to determine whether the shower that you are seeing is electromagnetic initiated or hadronic initiated is by the breadth, the width of the shower. So gamma ray generated showers tend to be much narrower than showers generated by nuclear fragments and nuclear particles. However, once you get to the very, very high end of the spectrum, the the nucleon showers can also be somewhat narrow as well. So again, you need to be able to sample a large part of the shower to really determine what's going on. Okay, so the measurements, the important measurements for air showers, the energy, obviously, the spectrum, and the arrival direction, which is important for astronomy. You can't have any type of astronomy unless you can do imaging, right? And in optical astronomy, lenses do the imaging for you, right? You just bend the light to a focus and you create an image and record it on an electronic detector or film. Although are there any film cameras left? I don't know. It's all electronic now, which is fine. The arrival direction, and so the techniques that many of the existing detection projects use are either ground-based detection in materials in which the shower particles pass through the materials, dump energy in the materials, and that generates light, and that light's detected, energy is measured. Or you look at the atmosphere for fluorescence of nitrogen, light from the fluorescence of nitrogen, excited by the shower, by the high energy particle shower. Sort of like a particle, sort of like a cosmic ray version, a high energy cosmic ray version of the aurora borealis. Okay, so here's in the lower there's a depiction of what a shower might look like. So the Fly's Eye project, which is now decommissioned out in Utah, had both ground-based detectors and a detector that looked at the nitrogen fluorescence. And so it's important to have these two different types of detection mechanisms because the different detection mechanisms suffer from different systematic errors. And so you can use one as a check on the other. So the detection of the shower at the ground and the view of the light, the Cherenkov light generated in the atmosphere by the shower, having the ability to do both of those is important for statistics. Okay, so again, sea level scintillation or Cherenkov sampling, the pros of that technique, it doesn't depend on the weather or diurnal cycle, the day-night. The cons, of course, is that only the shower has to be coming towards you in order for you to detect it. And your energy determination is model dependent because you're only sampling a portion of the shower. So now what you've got to do is you've got to do a Monte Carlo statistical simulation that takes into account all the possible particle interactions that could create a shower that gives the energy sampled by your detector, right? The other way to look for these is air fluorescence, right? The pros for that is that it's independent of particle trajectory, right? As long as you can see the atmosphere, you should be able to see the light, the fluorescence light, right? However, you can't do this during the day or on full moon nights, and it's weather dependent. And many of and again, much of the systematics for air fluorescence measurements deals with the understanding how light actually propagates in the atmosphere under different weather conditions, different atmospheric conditions. Okay. What's going on here? Okay. So, I wanted to share this with you because it's really cool. There's a website called the Chromoscope. And what the Chromoscope allows you to do is it allows you to view the sky in the different regions of the spectrum, right? And it sort of overlays, right? So you can look at the gamma ray, right? You can see most of the gamma ray sources as determined by the Egret experiment on the Compton Gamma Ray Observatory, and X-ray by Rosat, visible by Hubble, the hydrogen and near infrared by Sirleaf and Spitzer, and the far infrared and the microwave by Kobe and WMAP, and the radio, right? So this is really nice, but what's missing from this is the cosmic ray map, right? There's no cosmic ray map well developed enough well developed enough to add to this data set. And so that's what I would like to contribute to with this project. Okay, so here's the existing map of the ultra-high energy cosmic rays from the Auger experiment located in South America. So you can see the blue part is their sort of region of the sky that they can see. So they can't see what's in white, right? Which is an automatic bias, right, to their data. And then the shading, the blue shading, tells you where they're most sensitive to, right? So they're very sensitive area of determining the source locations of the astrophysical sources of the ultra-high energy cosmics is somewhat narrow. And now the circles, the black circles is basically their calculated source location so far. The red crosses is the catalog of sources, of gamma ray sources from various other catalogs. And so there's some indication that in some of these cases, the cosmic rays are coming from the gamma ray sources, but not always, right? And with a high degree of uncertainty. Okay, so obviously full sky exposure is necessary. So you can do that in two ways. You can either observe events from orbit, and there have been projects under consideration for doing that. In other words, you're actually looking at the atmosphere from orbit and then looking at the fluorescence, air fluorescence from cosmic events from orbit. Or extending existing ground-based experiments, such as Auger, will need to have a north version of Auger. Right now it's in South America only. A north version would give it a full sky view, but then funding is always iffy, right? And the National Academy and the Decadal Survey did not recommend the funding of Auger North. So that doesn't necessarily mean that Auger North is not going to happen, but they are not going to recommend to the President of the United States that it be a science priority. All right, so to increase detection coverage, improve statistics, right? So for the flux of the cosmic rays of energy that are higher in energy than 10 to the 15 electron volts, your event rate is about 2 pi times 10 to the minus 5 square meters per second. It's pretty low, right? And for the flux rate for the ultra high energy cosmic rays of 10 to the 17 electron volts or more is even less, 5 orders of magnitude less, at 10 to the minus 10 meters squared per meter squared second. So now, if you wanted to build a detector large enough, a ground-based detector large enough, in order to increase your detection statistics to a few events per second, you'd need a detector of area 10 to the 10 meters square, which is not that bad. It's actually less than half the land area of the Earth. Okay? So it's not totally cloudy, but clearly exposure is a challenge, right? Okay, so what can you do, right? Well, you could try to increase exposure by deploying relatively inexpensive detectors, right? So there were a number of projects, in fact, in your own backyard here in New York, started out of the Brookhaven National Laboratory, which I collaborated with. The Mariachi project, the mixed apparatus for radar investigation of atmospheric cosmic rays of high ionization. The WALTA project, the Washington Large Telescope Array, and the NALTA, the North American Large Telescope Array, et cetera, have all been sort of vertically integrated STEM education efforts to do both cosmic ray astronomy and promote STEM education at the K through 12 and the community college level. However, I kind of feel like we can do better than that, right? It may be, I think the technology is sort of, is at the point where you should be able to walk into a store and not only buy an optical telescope, but also a particle telescope, There doesn't seem any reason to me why you shouldn't be able to do that. So if you're going to do that, how are you going to do that? All right. So first thing is you use the internet itself as the detector network, right? So the network is the detector, all right? So here's a map of the inner density of the internet, right? You guys are much more familiar with this than I am. So if you can imagine, if a detector was wirelessly Ethernet addressable and could stream its data to the network, then that data would just be available, right, for anybody who is interested in detecting it. And individuals who are interested in operating one or more particle telescopes could provide that data to the network as well as do their own observations, as well as coordinate with other people across the internet to coordinate their observations as well. Okay, so what will be the requirements for doing something like this? So if it's ground-based, you're pretty much talking about detecting a ground-based box, right, the cosmic cube, that detects showers of cosmic rays primarily via scintillation. You should be able to measure the energy, the width, the time width of the shower front, and determine the shower zenith angle to a few degrees, and determine the time of the event, and it should be easy to use, right? You should not have to be Victor Hess or Albert Einstein to use this. Okay, so this was a project out of my lab at Florida A&M University. The principal people are myself and Michael P. Frank, who's the research engineer and technical lead on this, and I had a number of students who've come through the lab and worked on this from time to time. And I kind of think of my lab as a hackerspace because I give my students quite a bit of freedom to work on things that they're interested in, as long as there's some dovetailing with my interests. So I'm extremely flexible in allowing that. Jacob Billings, who was a biochemical engineer, and you might think, why is a biochemical engineer working in an astroparticle physics laboratory? So he basically worked on developing a device that used biological materials to detect light from particle radiation events. And he's in graduate school now at Emory. All right, so the Cosmic Eye project, which was a wireless sensor network for exploration of cosmic rays, of high-energy cosmic ray air showers, the idea for the deployment was to have 4 detectors, scintillation detectors, all sort of sending their information to a central timing unit that would determine coincidences between the 4 detectors and determine the time of the shower event and send that information to a central PC. And the idea originally was to use an optical syncing mechanism so that all the clocks, all the timing clocks on each of the detectors would be synced by a line-of-sight optical. Again, this started in my lab as part of a collaboration with Helio Takai, who's the PI of the Mariachi project, now primarily at Stony Brook in the Nuclear Science Laboratory, but it started at Brookhaven National Laboratory. Helio Takai is a staff physicist at Brookhaven. He actually is on the Atlas, the LHC Atlas detector team. Okay, so a particular node, you've got the shower particles that interact with the scintillator. The scintillator light is then detected by a PMT. The PMT then gets its pulses digitized by an FPGA-based time-to-digital converter, and then that data is sent wirelessly to the network or a central PC, or really any device that can accept the data and provide it to the network, or the detector itself. Electronics can just make the data available to the network via 802.11 standard, any device that wants to take a look at it. I'm sorry, say that again, I can't hear you. Photomultiplier tube. I'm sorry, yeah. So PMT means photomultiplier tube. So a photomultiplier tube is basically an amplifier for very, very small light signals. Light enters the front of the PMT, ejects electrons from a material called a photocathode, and then those electrons hit an electrode, and then that electrode spits out more electrons. Those electrons hit another electrode, and so on and so forth. You get a cascade until you get a measurable pulse out the back of the PMT. Okay, so the wireless module that we looked at for providing the wireless connectivity was the EasyUrio wireless module. In academic projects, the funding, the proposal cycle, and then the funding or not funding cycle is so long that by the time you actually get funded, the technology you propose to use is probably already obsolete, right? So there's probably much better wireless technologies that should be used for this now, right? So if we do this again, unfortunately, NSF did not renew our funding. So we're looking elsewhere. We probably should look at what is now considered really, really good state-of-the-art, but cheap wireless modules. So the important thing for the science, right, is the pulse shape reconstruction. So in the shape of the pulse, it turns out that different particles interact differently with the scintillation material, right? And so the shape of the pulse will tell you something about the type of particle that interacted with the scintillator material. And so it's important that the electronics be able to provide a pulse shape reconstruction mechanism. That can be done offline after you pull the data off. Or it can be done in the hardware, right? On the FPGA-based front-end digitization. Well, let's see, FEDM means front-end digital acquisition module. Yeah, okay. That's what my engineers told me to say. Okay, yeah. All right, everybody is familiar with what an FPGA is. You guys should be more familiar than I am with FPGAs. Yeah. Okay. So the digital front end for this is somewhat new because the traditional way of processing nuclear pulse data, right, from nuclear detectors and radiation detectors in general, is to have an analog front end that then gets digitized through A to D converters, and then you can do offline analysis on your computer after you've taken the digital data off. But the nice thing about doing this in a fully digital implementation on FPGA is you can do everything on the board in the front end. You can provide some analysis and even some filtering of events right there on the front end. And so that provides some flexibility of observation in terms of the kinds of cosmic ray events you might want to look for. Okay, so we presented a poster on the board that we developed with Brookhaven for this. And the board, basically so yeah, I'll just use the cursor here. So basically here are the signal inputs. All right, here's the FPGA chip, which is shown with thermal paste. We sort of borrowed a technique from the gaming community, right? We wanted to run the FPGA faster than it really should be run. So we overclocked it, right? But we had to cool it, right? Because it gets hot. And again, that's because proposal cycle funding. There are much better FPGAs that exist now. If we redesign the board with a current FPGA, we probably wouldn't have this problem. The FPGA that this was based on was the Stratix 2, which is the Altera Stratix 2, which we got for free from Altera, so that's why we used it. So big ups to Altera. They're not going to give us any more for free, but that's, we got one, so. Okay, so.
This is Michael Frank.
Stop.
And we are currently doing a test of our front-end digitizer board, where we're using it to digitize
Okay, let's start this over. Let's start over here.
And this is
Professor Ray O'Neill. So basically, we've
And
posted
we
all
are
of our
currently doing a
videos
test
of all of our tests of our
our
electronics
front-end
on
digitizer
YouTube,
board,
on our YouTube
where
channel.
we're using it to
So if you go to
digitize
YouTube and you search
real
APCR
PMT pulses for the
DRDL,
first time,
you can check out our tests, and you can make comments about, hey, you're doing that wrong.
which are natural
You know, you might
radiation.
want to do it
We
this
don't know
way.
exactly how much of each.
Or I don't understand how this
But
electronics
anyway,
works, what's going
The yellow
on
line
here.
on the screen is the signal from
Whoops.
Hello,
And
this
this
is
is
Michael Frank. We
I'm
can
Daryl
see
McGowan.
the correct process of
Sorry about that.
digitizing.
Okay, so I just included the videos because there's, just to show you. So that's what a pulse actually looks like, right? From the detector output. And here, basically, is essentially the digital information that allows us to encode the level crossings of the pulse. So the way we implement the digital pulse processing using the FPGA is that basically the FPGA measures the time that the pulse spins over various voltage thresholds. So again, the nice thing about doing this in a digital reconfigurable computing paradigm is that you can alter the DAC levels, right? And then you can also, do the pulse shape reconstruction right on the chip. Okay, so now the idea of the cosmic cube, the sort of single detector node, is a commercial evolution of the cosmic eye, right? So the idea is that the cosmic cube detects, it sends its information to devices, whether the device is a PC, whether the device is a tablet device or an iPhone. And in the cloud exists analysis software and other data services for analyzing the data, right? However, all of the detection data just exists on the PC nodes in a peer-to-peer like network. I was at another talk here and somebody claimed that peer-to-peer was going away. And I don't know if that's the case, but maybe the whole model for this doesn't make any sense if that's the case. Okay, so the Cosmic Cube features wireless standard data streaming to devices or the cloud. It is the GPS standard enabled, so each radiation detection event is time and location stamped. The electronics that we already developed for Cosmic Eye would be there'd be a version developed for the cube for real-time analysis, which would include some radiation species discrimination. And the community of users, right? The idea, again, another plus of basing the digitization of the signal pulses on reconfigurable computing is to allow the users the ability to go into the FPGA and alter the gelware, right, the hardware software definition to their interest or to their liking. And so the idea is to allow the crowd, right, to determine the best way to look for various kinds of cosmic ray signals, right? So now, what's the price target for something like this? So if you look at the high-end Pro-Am telescopes, optical telescopes, they can cost up as much as $20,000 or more, primarily due to the optics, right? We have a new telescope at the university that hasn't been installed in the observatory yet, but the vendor basically had the mirror atomically milled in Russia, right? At a facility that had been, after the end of the Cold War, right, this Russian facility had to find a use for itself. And, you guys may have heard the stories of, Russian factories that were spitting out tanks and airplanes and fighter craft are now making like pressure cookers out of titanium. This particular facility had to find a use for its atomic milling. And so now it's under contract, right? You can just pay them to atomically mill an optical surface to angstrom, sub-angstrom figure error resolution. Flat panel TVs, PCs, right, $2,000 or less. It's all based on commodity electronics. The Cosmic Cube will have some optics and some electro-optics, but mostly commodity electronics and some special materials. For instance, if you're going to determine the difference between electrons and nucleons, right, the easiest way to do that is through calorimetry, where you force the gamma rays or the electrons in the electromagnetic part of a shower to convert in lead or depleted uranium. Now, I don't think we're going to get a pass from the FDA on putting depleted uranium in a consumer device. But we might be able to put lead in it as long as the lead is fully encased in in some kind of epoxy, so that it's sealed, right? It's fully sealed. But we'll have to see. All right, so who would want a cosmic cube, right? So we think the same people that are already into amateur astronomy and are science and technology enthusiasts, folks in this crowd, for instance, might want one because possibly contributing to science is an exciting thing. And there's some precedent for this in astronomy, particularly in astronomy, for so-called amateurs, right? I mean, this guy was an amateur, right? Darwin. It could be even argued that Einstein was an amateur when he developed the theory of relativity. And David Levy, right, of Levy-Shoemaker 9, that discovered the comet that slammed into Jupiter. He's an amateur. He's not a professional astronomer. This fellow, whose name I forget, Tunney, I don't remember his last name, forgive me, but he's not a professional astronomer, and he's discovered 2 exoplanets, right? So he was one of the early discoverers, professional or amateur, of planets orbiting other stars. So there's a great tradition, right, in astronomy. There seems to me no reason why this can't be true in particle astronomy once the technology is made available to users. Okay, so in the development of the cosmic cube, basically what would you get? You would basically get a box, right, which contains the detector material volume, and then the electronics box, right, which contains the front-end digitization module, FPGA based, some power electronics, which you either could plug into the wall or you could power by solar if you wanted to put your module outside. And there's useful science in putting the module outside versus inside. For instance, if you put your module outside, then you're going to be seeing more of the electrons in the shower, whereas you put your module inside, then you're pretty much only going to see the muon component of the shower because the electrons will be absorbed by the building structure. And then, of course, GPS. And so the software, all based on open source, and at least the software allowing you to alter the functionality of the FPGA would be available to you as well, right? The only thing you would not be able to open is the detector material volume, the box which actually contains the stuff which the particles in the shower that converts the particles and the energy of the particles in the shower to light, right? Particularly if that's going to contain lead or depleted uranium. Okay, for the duplication of the front-end electronics, we're looking at various companies that will do this cheaply, like Sunstone. We're open to suggestion on this as to the best way to pursue this, whether the electronics development duplication should be done in an open source mode at the hardware level, or at what level open source should be in the hardware, at least in part of the hardware. I don't think we really don't have a good idea as to how to do that. We've started a Cosmic Cube project page in Facebook. I know that there have been some other social media directions talked about at this conference that are anti-Facebook. We're open to putting a Cosmic Cube project on such as well. If Facebook is sort of dying, we don't want to sort of solicit, ask for participation on a dying platform. But we also have a survey which is trying to gauge the interest of the public in participating in particle astronomy. And we would like you to go to the survey and fill out the survey if you have a chance. None of the questions are It's a Google Documents. It's a survey created in Google Documents. None of the questions are required, right? You're not required to answer any of the questions in the survey, but we would like to at least know at least try to gauge the general interest in participating in something like this is. So there's the web page, the URL for the website, y.ly/bp8. Okay, now the sort of the IT addendum to the talk. So I'm a physicist. I'm not a computer scientist. So you guys know more about this than I do, and forgive me if I relate anything insultingly obvious to you. But the other possibility, let's say you're not interested in just using the box, the cosmic cube, as an astronomy device. What else could you potentially use it for? Well, you could use it to generate random bits for cryptography, for instance. In fact, the entire network, right, of users of these things could form an encryption network, right, a key generation network, or a random bit generation network of true randoms. Am I, okay. I've got 2 minutes left. Okay, very good. All right, so there are a number of random features of cosmic ray detection events, right, that you might use to generate random bits. So for instance, you could use the actual time at which the first voltage threshold is crossed by the pulse during a detection event, or the calculated pulse centroid time, right, which is obviously related to the first voltage crossing time. The counts per bin, as long as you create the right bin, right, the counts per temporal bin in observing cosmic ray events during the day, during the week, the month, years, should be random. The I-fold or J-fold coincidences, if you happen to operate a number of detectors, right, all tied into a single electronics box, because you want your own mini telescope to do triangulation on source direction, then the pulses that are not coincidence pulses versus the pulses that are coincidence of a certain number of coincidences should also be random, right? And you can think of a number of other things to pull that you can pull out of the data that would be random, that might be usable for key generation, for cryptographic key generation. Okay, so the detector network would essentially create a network random number generator, and you could randomly sample. There could be software tools made by the community of users to randomly sample data in the network nodes to provide another layer of randomness, right? And that could be used for cryptographic key generation following the recommendations, such as the recommendations made last year by NIST. With that, I'm just going to give a shout out to the funding that we've had, but the funding is going away. Right, Intel and Altera, our license. So we're thinking about going to Kickstarter, Indiegogo, or Rocket Hub, and of course we have a Bitcoin address. So if you are inclined to support us, to participate and support us, you can Bitcoin us at that Bitcoin address. You can also contact me at that address. I'll leave the Bitcoin address up. It'll come back up in a second. Okay. 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 Thank you, and I'd like to thank the Hope Committee for allowing me to share this project with you.